she's back here on my desk. No, yes. I guess I should say she. But I have my Matryoshka. And we're trying to think about outer, we're trying to think about inner. So, how many Matryoshkas, Russian nesting dolls, would I need to use to illustrate the very first function? Just 2, right? Because what's the outer shell? What's the outer function? What's my f of in my composition? My f of x, or we could change the inside to be a u. It makes some of your brains deal with it a little bit nicer. What would my f of or my outer shell function be? U to the 5th. Yeah, something to the 5th. What to the 5th? I don't know. Let's go ahead and see. What to the 5th? Oh, who's inside? Who's this guy? 3x plus 2. Now, if I was to go any further, what would be the only thing inside 3x plus 2? Technically just x. X is inside. But x's little derivative is 1, so we don't really stress about him because he's pretty basic. So we have our outer shell, our u to the 5th, and our inner shell, 3x plus 2. Now, how about for the second one? What'd you guys write as your outer shell? Your f of x, but we could write it in u notation. Is it easier to think of the outside or the inside? You could technically do either order. Did anybody see the inside first? No? Everybody looks at the outside? Okay, so what was the outside? Sine of who, though? Maybe we should look at the inside and say u is 6x, and then the outside is, well, okay, fine, sine of 2. Let's see if that makes a little more sense. So let's try it on this one. What would u be? X squared plus 1, and what would f of u be? You could do square root of u, but why is Adam saying u to the 1/2? I think he's thinking ahead to power rule, maybe how it needs to be done. So. What? Derivatives? No. There's no derivative language yet, but we are in calculus, yeah? Okay. How about the last one? Now that we've rewritten it, it's a little bit easier. Who is my, let's think about the inside. Who's my inside? X squared. And then my outside could be, okay, so let me see if you actually have the idea. You ready? So we're about to give you something like, how about decompose? One more example. 1, 2, 3, 4, 5. Y is equal to, let's do 3 over the square root of sine of 3e to the 2x. May as well have some fun. I think there is an h of x. Sometimes instead of looking at the outside and trying to peel off, sometimes it's easier just to say, okay, well, hold on, who's innermost? Sometimes instead of starting on the bigger and then peeling, sometimes it's easier to think who's the innermost and then what does he go in? And then what does that go in? And then try to put it together like that. So let's go looking for the innermost. Who's the guy who's stuck the most in between? Not just e to the, I would say 2x. What do you guys think? E to the, not x, but e to the, okay. So, do you think u is going to be enough of a letter? No. So let's go v. So if v is equal to 2x, then who could my u be? What's right outside of the 2x? 3e. Yeah, 3e to the, well, can't we say e to the him? E to the v?
Well,
and what's outside the 3e to the v? Uh-oh. I'm supposed to be done with sine of, but I'm not done yet, am I? Guess what? There was a w. So w is 2x. T-U-V-W. V is equal to 3e to the w. U is equal to sine of v. Are we good so far?
Yeah.
So that's inside that, and that's inside that, and this is inside. There we go. 3 over square root of u. Oh, wait. Oh, that's okay. 3u to the negative. Now, do you see how it gets messy if we don't exactly know how many letters there is? There are. Oh, awkward. So maybe starting on the innermost isn't always the best idea. I mean, if there's just one innermost, sometimes it makes it easier, but if there's a lot of innermost, it gets a little bit nastier. So let me give you guys one more, and I want you guys in your groups to try to break them down. But maybe, it might not be the best strategy if there's a lot of letters to start on. Maybe you should start on the outer and then kind of build your way down from there. Let's see. What if I were to give you something like, okay, let's do y is equal to tangent of the square root of 3 plus let's just do something basic again. 5e to the x squared plus. Okay, go. Start with the innermost, then you need to figure out what letter it is, and that's kind of complicated. Maybe it's easier to start with the outermost and build your way down.
So you just go letter by letter down?
Yeah, I think I would. I think I would start with F.
I think of you.
And then ask yourself, well, who is you? And then ask yourself,
I am you.
And ask yourself,
You is mine.
what? I think it's me.
So it's what's the fuck? Jackie Chan.
That was even selfish. Can you get talk out your groups?
And then D is 5e to the W. Yeah. And W is x squared plus 1. That's the other way. Going inside.
Misty, is that one of our problems? No, I was the one editing.
Kyle.
I randomly wrote up and someone actually answered it. That's terrible. Product answer.
It was it. It was enough to scare people. Now we're getting rid of this.
It was just that fun.
Yeah. He was just trying to make, for me, a really nasty problem. All right, you ready? Did you guys see that tangent was the outer shell? Right? It was tangent of the. It's so nice when we do these because you can just be like the and just ignore it for a bit. A lot of people like saying tangent of. After you watch this video at the end of the year, which is all of calculus, like the whole year, kind of, not the AP year, but the whole year basic stuff. There's a guy who does calculus in 20 minutes. He just like, and he uses Play-Doh, and he's like, chain rule, you just talk about a block. It's tangent of block. And then you have to think about the block, and then say, okay, well, what is the block? Well, U is equal to, anybody get square root of V?
Yeah.
Because we'll peel off. Remember with a matryoshka? So with a matryoshka, you gotta peel off. Onions have layers, peels. Anyway, peel off. Matryoshkas, peel off the outer shell and say, who's underneath? So John, ready? Peel off the tangent. Who's this? A square root of who? I don't know. Block.
That's why I put square root.
Yeah, you see it? Just block. Just block it. Now we have to deal with that and say, okay, well, who's the block? Well, it's 3 plus 5 e to the w. Because it's tangent of what? Well, square root. Well, square root of what? Well, square root of that guy. Well, who's that guy? Well, it's 3 plus 5 times e to the... Then w would have equaled x squared plus... Don't stress about if you got it right the first time. Does it make sense now? You see it?
Yeah.
You see how I just kind of keep on doing more and more parentheses? Right? So I have tangent of, that's my outer. Then I have square root of, that's my next. Then I have 3 plus 5 e to the of And then what would my last one be? Well, if I wanted to do it, it'd just be x, so it doesn't really make a difference. As soon as I get to my x, I'm like, I'm done. As far as decomposing, now we still haven't taken the derivative, but if you can break down a function.
I'm just kind of speculating, just throwing theories out there. Could v equal 3 plus w? Or would that not work?
In pre-cal last year, there were lots of different ways of decomposing a function, but this year, let me show you what we need to do with the derivatives and why this is the only way we can think about the decomposition getting ready for the check. Does that make sense? Yeah. So in your brain, you're like, well, I could have made this work. Yeah. So what we want to do is every time there's an of, we need to break it down. So tangent of, break it down. Square root of, break it down. 3 plus 5 e to the is like an of, it's an argument, break it down. And then it'd be, well, what's the argument of x squared plus 1? Well, it's just x. So we're okay. But yeah, in pre-cal, you're right, there were lots of different variations. But let's figure out who this Chimu guy is, and then come back to all of these. So how to derive? Let me just go to a single page. Let's get, I'm saving that. Yay, it's saved. Okay, so, given f of u. Let's see. Our goal in all of these is to get a dy dx. Okay? That's our goal. At the end of the day, what we want is a dy dx equals. Our goal is a dy dx equals. But did you guys realize that just a second ago, we didn't have y equals f of x. Well, we did. At the very, very beginning, we did have y equals f of x. But what I'm telling you with all this decomposing stuff, we had y equals f of x. So the problem was there was an inner within an inner within an inner within an inner. Okay. So if we decompose this function, we don't have an f of x, we have an f of u. We don't have a u of x, we have a u of v. We don't have a v of x, we have a v of w. Finally, we have a w of x. If I was to rewrite all of this, guys, technically what each of these would be, now we don't do it because it takes a long time, but this would be a u of v, this would be a v of w, this would be a w of x. Whew! As soon as we get to the x, we're done, as far as decomposing. But how the derivatives work, well, it's a little bit trickier, because if we were to take something like what we just had, if we had something like we had an f of a u of a v of a w of an x, which is technically, oh dear, done. Okay, super overwhelming when you look at it like that, right? Like that's disgusting. But just a second ago, was it all that crazy hard to think about what each of the different layers were? No. Not if you decompose them and break them apart. Let me show you how the math works. If we were to take the derivative of the f of u, we would actually end up with dy du. Now, is that dy dx? No. If we were to take the derivative of the f, that would be a dy du, because he's in terms of u. Well, that doesn't work. Let's keep on going. What if I was to take the derivative of u? Well, wouldn't that be a du dv? What if I was to take the derivative of the next guy? Wouldn't that be a dv dw? And if I take the derivative of the last guy, wouldn't that be a dw dx? Now look at this and think, what operation could we do to derivatives of each and every piece of the decomposition to get what we want? Not even cross multiply. Cross multiply means it equals and we go across the equals. Why not just multiply? Check it. What's going to happen if we multiply? But we have to take the derivative in a very particular way, where we think about outer and inner functions. In our mind or literally on paper, we decompose them. In our mind or literally on paper, we decompose them. And Kyle, if we decompose them in this way, where every time it's literally a composition of. And each of those pieces individually we can derive with basic rules. Check it. Can you derive tangent of u? Yeah. Can we derive square root of v or v to the 1/2? Yeah. Can we derive 3 plus 5 e to the, not x squared plus 1, but e to the w? Yeah. Can we derive x squared plus 1? Yeah. If we can decompose it into smaller, differentiable pieces, all we got to do is, wait, what operation did we just see that we need to do? Multiply. So it's all about multiplying. The derivatives of the layers. It's all about multiplying the derivatives of the layers. Each and every matryoshka needs their derivative. Now, this gets a little bit tricky, a little bit sticky, a little bit confusing if you don't decompose. So if you guys don't mind, can I do a really hard one? Like the one that we just saw, can I derive that guy and then can we go look at easier ones? Is that okay?
Yeah.
Let's do like the worst of the worst of the worst, which technically if the AP was to talk about this, it wouldn't say f of u of v of w of x, that's awkward. It would say f of g of h of, not I, that's an imaginary number, j. F of g of h of j of x. It wouldn't use u's and v's, but in my head it just makes a little bit more sense to be using u's and v's. They would use a little bit different notation. We'll learn that notation so we can be ready for their problems when they come, but for right now we're just getting the idea. Let me go back to the one that we just did. Given this idea of the chain rule, and then let's start working it out as far as making it simpler for smaller problems. So this guy, if we were to follow this technique, okay, of deriving the layers. That's not what I wanted. Sorry, I was saying I want dual page. There we go. If we were to take this technique of deriving the layers, who do we need first? We need f of u's derivative, right? So f prime of u to get our, right? To get our dy, oops, I don't want it. To get our dy du, we need to go ahead and find f prime of u. Well, actually, let's not worry about notation. I just said we weren't going to worry about notation. I apologize. Okay, to get our dy du, we look at the guy in terms of u. It's this guy, dude, right?
Yeah.
This dude, right? Anyway. Wouldn't that be secant squared of u?
Yeah.
You have to know your derivative rules to know that one, right? But we have those new trig rules. So we're taking the derivative of the outer matryoshka and saying, what's your derivative? Secant squared! Yay! Now it's time to tackle the u, right? Okay, what's the guy in terms of v's derivative? Well, okay, hold on. We could rewrite that to be v to the 1/2. Wouldn't that be 1/2 v to the negative 1/2? You guys agree?
Yeah.
Sweet. Who's next? dv dw, right? His derivative is going to be, what's the derivative of any constant? What's the derivative of, well, the 5 stays, but e to the w, isn't that just e to the w? Don't they just stay the same? Sweet. And then what's the last guy? 2x plus 0 is just 2x. Now, guys, even though technically, yes, we do have dy dx, here's the struggle. Oh, sorry. Even though we do have dy dx, here's the struggle. Is this in terms of x? There's a lot of nesting. There's a lot of nesting. What do I mean? There's the x.
Also w.
But there's there's w's and v's and stink. I have to remember who these guys are? Yes. So here's the strategy. Ready? Here's the strategy. Start at the top, work your way down. Meaning, secant squared of u, well, who's u? Isn't u just the square root of v? Times 1/2. Well, can't I rewrite this to be 1 over 2 root v? Is that okay? I'm just going to rewrite. Okay. Hold on. I'm not done yet. Now I have to go tackle all the v's. So who are all the v's? Secant squared square root of, isn't v 3 plus 5 e to the w? But don't I also have a v here? 3 plus 5 e to the w.
Whoa, I don't think that's at all.
Uh-oh. And now I have to go figure out who w is?
You have 3 spots for W?
So then I have, well, hold on. We could start putting all of our fractions together. Do you guys want to do that? Make it one big old fraction?
Yeah.
Okay. So then we have on top a secant squared of a square root of 3 plus 5 e to the, who was w again? Oh, x squared plus 1. We have a 5 e to the w, which 5 e to the w is x squared plus 1. But then we had this little x dude. I guess x's usually go in the front, so I just put this here. And I'm going to go ahead and reduce that too, because isn't there? Okay, so I can do 5 and x and e to the x squared plus 1, and then I have times my secant squared of my blah, blah, blah. My 2's can reduce, that's nice. And then I have the square root of 3 plus 5 e to the x squared plus 1. Guess what? Some of my secret kitten killers, what would you really want to do? Except what's the problem? Isn't it secant squared of?
Yeah. That would be just a sec.
Yeah, you can't just have a sec. I mean, you can, give me a sec, but number one, we never mean it when we say it. And number two, yeah, I can't just have a sec. There is another approach, there is another way of going about this. I'll show it to you in 1 second, but Adam, go ahead.
So going from the top to like your e by dx, I get how you rewrote the 1 over 2 e, but how did you go from secant squared e to secant squared square root e?
Because u is square root of v. Oh. See it? So I went through and said, all my u's, you become root v's. All my, then my next step, v's, you become 3 plus 5 e to the w's. And all my w's, you become x squared plus 1's. Woo! Finally, we have it all in terms of x. See it? Now, do you want to see how I and most BC kids would have derived this? This isn't wrong, this isn't bad, and this is exactly showing you the concept of if we decompose a function, we just have to take the derivatives piece by piece, but leaving all the nesting in there, piece by piece, leaving all the nesting in there, so then at the very end, we just have to go ahead and go plugging in what all those pieces are to get to our in terms of x derivative. But here's how I would have done it, because here's another approach to the chain rule. Another approach to the chain rule. Actually, you know what? I think I have a page of notes on this. Hold on. We've done the f of u approach. Let me go ahead and delete this page real fast. We've done the f of u approach with our original function. Let me quickly, I think you guys should be able to follow. It's really hard if you don't do the video, because I kind of do things out of order sometimes. This page is what got us to this derivative, right? We did the derivatives piece by piece by piece by piece and multiplied them all together and then got them all in terms of x at the end. There is another approach. Let's not do that one yet. Where's my other approach? ¿Dónde está? Oh no. I don't want that one. Okay, I'll just show it to you. I have it, but it's for another example. Here's the inwards, right? And this is also the all at once way. Which you can think about it. We've done a lot of like, okay, do this, and then go do this, and then go back and do this, and then finally, okay, you get an answer. This is the all at once way. Derive the outer, keeping the inner. Times the inner prime. In words, the chain rule basically says derive the outer, keeping the inner, and then times the inner prime.
I like that.
Keeping the inner. And then times, the multiplication breaks it out, times the inner, whoop, oh no, the inner prime. I'm going to do it with the really nasty one, and then I have a really easy one coming, so hang in there. Derive the outer, keeping the inner, times the inner one. Remember how we said that tangent was the outer? From my experience, I would look at this and see, oh, tangent's the outer. What's the derivative of tangent? Well, because I'm really good at my derivative rules, I would say secant squared, but then I would keep the inner the same. Square root of 3 plus 5 e to the x squared plus 1. All my matryoshkas are still nested. All I've done is derive the outer. Everybody's still inside, keeping the inner the same. Now, ready? Times. Ha-ha! I get to break out a layer. Okay. Tangent's gone. Whew. After the times, the tangent's gone. What's next? What was our next piece? Square root. So now I'm ignoring the tangent. I already dealt with him. Derivative of the outside, keep the inside the same, times derivative of the inside. Derivative of square root of blop is, well, 1/2 blop to the negative 1/2, or 1/2 square root of will keep his inner the same. Okay. 3 plus 5. E to the x squared plus 1 times, aha, I get to break out of the square root. I'm going to run out of my short screws. Who's the next guy? Dealt with the tangent. Check. Dealt with the square root. Check. Who's next? 3 plus 5 e to the blop. What's the derivative of 3? 0. Plus, what's the derivative of 5 e to the blop? 5 e to the, who's the blop? Keep it the same. Then times, okay, if I could, I'd break it out. Yay, who's left? X squared plus 1. And what's x squared plus 1's derivative?
Good.
Do you guys see any similarities to what we just got?
Yeah.
But what did I do?
I like that one a lot better.
I did it all in one shot.
I like that better.
It's nice, but you have to get the hang of it, else.
That's a lot.
It's brutal.
Because
But do you see where the idea came from?
You don't have to keep track of all.
You don't have to keep track of all the letters and all the blah. Now, guys, to be honest, this is like one of the worst ones you'll ever see as far as just chain rule being bad. Like the F and the U and the V and the W, F and G and H and J. Like, what the heck? But do you see the idea of outer? Keep it times, okay, break it out, I should say. Derive the outer, keep it times, break it out. Derive the outer, keep it times, break it out. Derive the outer, keep it times, break it out, derive that. Now, you don't have to have this way. Those of you guys that like formulas, to be honest, this way is the safe way. This is the way that I tutored a kid a few years ago, and his math skills were a bit rough. But where I had top kids making mistakes on chain rules, he could do something like this, doing this method, and he would get it right every time. And he had issues with like adding and subtracting and things like that, but he could do a chain rule because he used this method. The kids that like the shortcuts are the ones that are going to make the mistakes. That's the rough part. But do you see how the, well, sadly it's like 2 pages away now, isn't it? But do you see how my method and this method both got the same answer, right? So let's do an easier example. Thank you for hanging in there. I know it was rough and I know it was overwhelming. You do not have to, at this point in time, you do not have to have the chain rule totally figured out. Just realize there are different ways of doing it, and let's talk about those different ways. So let's go back to something easy. Ready? Let's go back to something easy. Good. Well, some of you, that's all you need to be able to basically tackle this entire homework. Some of you, though, you're like, I think I kind of, don't worry, here you go, let's do it easy. So wasn't this one of our first decomposition ones, guys, that you already thought about? As far as an outer and an inner? We're going to use the U and V form, and we're going to use the words. Don't worry, there's still that whole, the AP does it a weird way. We have to talk about that, so you can be ready for it. But for right now, just the idea. Okay. If I was to say my F of U form, or if you want, you can think of your Y form. Couldn't I say Y is equal to U to the 5th and U is equal to 3x plus 2? You guys agree? And couldn't I do my dy du times du dx? Not that you have to write this every time, but it'd basically be, well, just do it, right, guys? What's the derivative of that 2? 5u to the 4th times 3. And then ask yourself, well, who is u? Use 3x plus 2. So wouldn't it be 5 times, well wait, 5 times 3 is 15, yeah? Oh, sweet. So you get 15 times who to the 4th power? 3x plus 2. There is my dy dx. Let's check out the word form. Can you guys write those words down? What's the idea of the chain rule word?
Drive outer, keep inner, times inner prime.
Okay. So we go straight to dy dx. We have to ask ourselves, well, who is the outer? Fifth power. Block to the 5th power. Well, how do I derive block to the 5th power? Derive the outer, I bring down. But what do? Do I break it out yet? No, so I keep it in. And then times, break them out. Ha ha! 3x plus 2. What's your prime? Huh. Dun, dun,
That is so
dun, dun.
much better.
They both work. This one's super nice when you have U's and B's and W's to help your brain just kind of decompose for a bit and then bring it all back together. Less than that. Sometimes God breaks it down. But anyway, give me that. The words are good, but the words are dangerous. And can I tell you the most dangerous part? The thing that I keep on saying again and again and again and again and again, and I've only even done the words a couple times. What do you have to keep unchanged? We'll talk more probably tomorrow about why I call this the bunny rule. Yes, you can kill bunnies by messing up the chain rule. It's the whole thing back here to poor little bunnies. They die every day. The reason why I call it the bunny rule is because Fibonacci, and you know the Fibonacci sequence, the 1, 1, 2, it was all because of bunnies and how bunnies multiply quickly that Fibonacci thought of this whole thing. Bunnies multiply quickly. If you've never
Utopia.
Yeah, they have like a ridiculously short, what's it called, maturity time, whatever, like, it doesn't take long for bunnies to be able to produce kids, basically. So, anyway, bunnies multiply, it's ridiculous. Bunnies multiply! Chain rule multiply, there you go, it's good. So then we start talking about abortions and like how you, no, keep them inside, and then, okay, now it's the proper time to break them out, and it's a whole mess. Long story short, take the derivative of the outside, keep the inside the same. But as soon as you multiply, then it's time to break it out, then it's time to take the derivative, then the proper time to go ahead and deal with the inside. Anyway, we have a forever card. That forever card, okay, there's this f of g of x form. Let me actually talk about him after we talk about the forever card, because this is where the AP guys start getting really technical. So pause, let's talk about the forever card first. Chain rule, the derivative of a composition of functions. I'm going to start with what you know. And what you know is, okay, just a super basic one. A super basic one is just an f of g or an f of u. No v's, no w's, no whatever's. Just an outer and an inner, like this example right here. One outer, one inner, that was it. 2 matryoshkas, that's it. And we would have done that by saying dy du times du dx. That would have gotten us there. Which in essence would be, technically, our f prime of u times u prime. Oh yeah, that's a thing. Which would technically be our f prime of u times u prime.
U prime.
Exactly. F prime of u, derivative of the outside, keep the inside the same, times derivative of the inside. That's a notation for what we're doing. In words, it's what I said before. It's the derivative of the outer. Did you guys see why I'm putting parentheses when I say keep the inner the same? Because it's always inside. In the parentheses. Yeah, in the parentheses we don't touch. Keeping the inner the same. Huge, huge, not factorial, but exclamation point there. Times, as soon as we multiply, now we can break out the inner and take his prime. I guess we could even put like a d in there and have it be like the particle quotient rule. D outer, keeping inner, times d inner. I don't know, it doesn't sound as good as particle quotient rule. Derivative of the outer, keeping the inner the same, times the inner prime, times the derivative of the inner. But if we were to write that the snazzy way, we wouldn't be writing u, we would be writing g. So it would be f prime of g of x times g prime of x. That's the snazzy way of writing it.
Whoa.
F prime of g of x times g prime. But it's just a derivative of the outer, keep the inner, times the derivative of the inner. But this top one is the easiest one to be able to show what you would do with any composite function, no matter how nasty. Because once you get into a rhythm, as long as you understand it, it's not that bad. Because you just derive the outer and you keep the block inside exactly the same until the times. And then you peel off and say, who's next? All right. Keep it the same. Who's next? Who's next? Well, if you peel off the h, don't you just have the x? And isn't the x derivative just 1? Yeah, we're done. You derive and you derive and you derive until there's no more peeling off. You derive, you derive, you derive until there's no more peeling off. This is forever card. Ah, Adam, where are we at? 16? Oh, 15? Oh, 12, 13, 14. And we didn't have to do acceleration because we already did it. That's right. You need to update your cards online so you guys can be writing them and studying them, huh? Bunny rule, because bunnies multiply. Hopefully yours won't. Forever. U prime. Do you have a U? You need a U prime. But that U prime is after a multiplication, hence the bunny rule. How many bunnies are going to die in the next couple weeks? Throughout the year?
Oh boy.
A few. Million. Anyway. Let me show you then that third notation that I was keeping. According to the AP, we could have written this as, and this is where it gets confusing, f of x is equal to x to the fifth, and g of x is equal to 3x plus 2. I don't like this notation because it's hard on your brains to realize this x and that x in a sense are different. And so they would say that the derivative of your f of g of x would equal your f prime of g of x times g prime of x, which would be 5 times who to the fourth? Well, g of x to the fourth times g prime is 3. And then you would have to go find who is my g of x. And you would get the same answer that we got in all the other versions. Now, not that the AP necessarily makes you write it like this, but do you guys remember numbers 109 and 112 from the homework we graded yesterday? Remember how they gave you some random points, but they weren't random at all, and they gave you some equations without real equations, and it was all notation, and you had to know what to do? I'm preparing you for that one, too. Because they could do the same thing. So, we have a few minutes. Oh, we already did that one. That's no fun. Let's get rid of him. We're tired of him. Let's do some more. You guys ready? Okay. The one notation I'm probably not going to do a lot is the f of g. I like using my words, and I like using u's and v's. Well, this one, neither of these need any v's. All they need is u's, right?
U.
Because can't I just say something like, my y is equal to sine of u, and my u is equal to 6x, right?
Yeah.
So couldn't I say just derivative of, well, you guys help me out. Come on, I can't do all the work. dy dx, how does this work? Yeah, what do you think, derivative of the outside, or what do you think, derivative of the outer layer? Either one, it's cosine. Cosine of who? Well, technically u times u prime is 6. But if you were doing my outer inner trick, wouldn't you have done derivative of the outside, keep the inside the same? Now, question, does this make it 36x or 6 cosine?
6 cosine.
Yeah. Yeah, this is my cosine function. I have times 6. That's a coefficient, right? That's a coefficient. So whether you use mine and then say, oh, his derivative, and then plug in, or whether you take derivative of the outside, keep the inside, you just skip a step. So can you guys find me the derivative for number 3? Anybody have one yet? You don't know where that came from. You don't know where that came from. That came from. Bring down a 1/2, negative 1/2 power, pops the square root in the denominator, and then you go ahead and plug it in and simplify it. How we doing? Was it too mean to give you a radical one? Sorry. Didn't mean to be mean. The nice thing is, kiddos, if you ever see a u to the n, like this one, u to the 1/2, you can always think power rule. 1/2 u to the negative 1/2 times u. And that might even make it shorter. So what we're going to do is start looking at all of our derivative rules with u's and realizing, well, with a simple u, it's just u. Bye, get out of here. You're bad. So easy, kids. Learn about u. You just cracked my whole back, okay? It was a monumental day. Mark this down in history. Wednesday, October 3rd. You learned the chain rule. Bye, guys.